Hi, welcome to the third lab of the Serverless ML course. In this lab, we're going to cover training pipelines, batch inference pipelines for a credit card fraud example, and we're also going to go through some model-specific transformations. In particular, we're going to look at label encoding a target variable. Let's get started. And what we're going to cover in this lab is we're going to, firstly, we're going to start actually with model-specific transformation in scikit-learn. We're going to take the iris flower dataset that we covered in the first lab, and we're going to encode the label. So if you remember in the iris example, the label was the type of flower that was predicted based on the four features: the petal length, petal width, sepal length, sepal width. And it was going to be one of three iris flowers. So we had setosa, versicolor, and Ververica. It wasn't actually Ververica, but it was something similar to that. I can't remember the name. But in any case, we're going to start with that, and then we're going to go on to look at writing a training pipeline with feature selection in a notebook. So we're going to go to the credit card example, and we're going to go back to that. We're going to select some features from our two feature groups. We're going to create a feature view. We're then going to create training data from that feature view, and we're going to train a model. And we're going to register that model in the model registry. So that'll all be in one notebook. And then finally, we'll have a batch inference pipeline. We'll write a batch inference pipeline to make predictions on some new features that we're going to write to the feature store. And we're going to write some new credit card transactions to the feature store. So we're going to write them to our two feature groups from the second tutorial. And we're going to make predictions about these new features that we've written. So new credit card transactions, we're going to predict if they're suspected of fraud or not suspected of fraud. And then we can finish it off by implementing a batch inference pipeline as a GitHub action. So let's get started. And the architecture for what we're going to do today is basically we're going to train a model, register the model with the model registry in Hopsworks, and we're going to have a batch inference pipeline that's going to make predictions based on new features that have been written to the feature store. And we'll orchestrate the execution of the batch inference pipeline with a GitHub action, and we won't orchestrate the training of the model, because training can happen kind of asynchronously in the background when you need to train a new model. We don't think it's something that needs to be orchestrated. It's not an operational system in the same sense that a batch inference pipeline is, which would need to make predictions today or this hour. You need to write your features today or this hour, but models can be retrained when needed. So the first thing to do is to go to your cloned version of the GitHub repository for the Serverless ML course. And if you haven't added an upstream remote, add it. And then you can pull any changes, because we've made some changes since the last lab. We've added the new modules. Now I'm going to start by looking at the model-specific transformations with the iris flower example. So let's look at what that is. So in this case, what we're going to do is we're going to open a notebook called iris with sklearn transformer.ipynb. So it's a notebook file again. And what we've done is we've taken the tutorial from the first lab, and we've added label encoding to it. It's like modification to the lab, because in the first one, it printed the image of the flower, and now we're just going to print out the name. And what we're going to do is we're going to take the target variable or label, and we're going to encode it with something called the label encoder from scikit-learn. So this is this object here. So we're going to create a label encoding object, and then we're going to take the label, which is this variety column, and it's in our training set. This is the label Y. And what you do is you basically call label encoding object fit transform on this column in our train set. So the label column in our train set, and we're going to get back then the encoded labels. We also need to do the same to our test set. So we need to encode the labels in the test set. That's Y test is our test set with labels, and the column's name is variety. So we call le.transform on it. And then we get back our two label sets, from the train set and the test set, and they're both encoded. So that's what we're going to use when we're training the model, and also when we're evaluating the model. So seeing the performance of the model with the test set. So one thing that we'll look at is when we create a label encoding object, we want to make sure that that label encoding object, when we use it when we're training, so we're going to use it to encode samples or labels, in this case labels, when we're creating training data, And we're doing it after the feature store, remember. So we've done some pre-processing before the feature store. So we can do aggregations, we can do, we can do data compression, we can do binning and so on. But after the feature store, as we talked about in one of the earlier lectures, and in lecture 3 in particular, we talked about transformations happening after the feature store, where we might want to take a numerical feature and normalize it, or we might want to take, in this case, a categorical feature. So our label here, the variety of flowers, a categorical feature, and we're going to turn it into a numerical representation. Now, many models will need numerical representations for all of the features and the labels. In this case, k-nearest neighbors classifier doesn't, but we're just doing it for fun because it's a learning exercise. And what we'll do is once we've used, see this LE object, which is our transformer object, when we're in the training phase, we're fitting the training data and the test data to this LE object so that it knows all of the categories that are available. We want to make sure then when we're using this model in inference, so in online inference, so in an online inference pipeline. In this case, we're not using an online inference pipeline, but in general, when you're using an online inference pipeline, you want to use exactly the same object, the same label encoding object to apply the transformations on the features that come in inference. Because the set of categories, so the number of categories that were encoded in the training set, we want to make sure that if a new category arrives, for example, in production, well, maybe we want to either map that to a kind of a bin category where we'll dump them to, or we want to give an error and say, look, I've never seen this category before, so an error will be thrown by my label encoding object. Now, so what we want to do is we want to save this label encoding object to the model registry along with the model. This will ensure that when we use the label encoding object in our online inference pipeline, we get back exactly the same encodings. So it's a very easy way to do this is to use the joblib library to dump your label encoding object in the same directory as where your model is. And then when you're in an inference pipeline, you'll download your model and you'll also get this pickled, in this case, encoder object, label encoder object, and we can unpickle it using joblib again to load it. And then we can use that object then to actually perform transformations, and even something called an inverse transform that we're going to see. So an inverse transform is when we get the prediction as a number, but we want to turn it back into the string. So in this case, we'll get the prediction of which flower type it is, and we want to find out, okay, what was the name of the flower? Because there's no use on a user interface showing you that you predict that it's a flower called 0, when in fact the user wants to see it's Setosa. Okay, so without any further ado, let's look at this example from the repo. So I have it open here. So it's called Iris with sklearn transformer. And if we go back into here we can see it in here. We'll just pull this over here. It's in module 03, and it's Iris with sklearn transformer. Just close this alone here. Okay, so we can run through it briefly. I think it goes pretty quick. So in this case, it creates some feature groups, same as before. We get a feature view, we get some training data. And this is where then we have the change code coming in. So you can see here what we're doing is we're importing from scikit-learn a pre-processing package in this case, or module. Sorry, it's a module. And inside it, we have this object called the label encoder object that we're creating an instance of. So with label encoder object, we're fitting it to the labels, from the train set and the test sets, and we get back our encoded labels from the train and test sets. So when we want to fit our data, we're not fitting with Y-train anymore. We're fitting it now with the encoded set of labels. So that means when we make a prediction later on here on our input features, what we get back, Y-pred here, will be in fact the encoded predictions, not the strings, the categorical features we won't get back. So when we want to check for the performance of our predictions, for example, we would, in this case, we're getting the mean squared error, and and that's our performance metric here. Even though it's classifier, you can still use mean squared error in this case, because it's k-nearest neighbors. So in this case, we're going to compare the performance of the predictions, which are now encoded, with the actual encoded labels from the test set. And okay, let's see how we're going here. Okay, so now it's currently creating some training test data, and so we'll get there in a second. Okay, so let's go down and look at what else we need to do. So I said that we're going to save this encoder object along with the model in the model registry. And the way we do that is that we create a directory locally called iris_model, and then we just call job_lib dump. And we dump both of our objects, our pickled Python objects, the model and the encoder object, into that directory. So now when we register the model with the model metric, so it says metrics not defined. Maybe I missed this particular cell. Let's go back and call it, and then it should work. Okay, so now it's working, and I'm saving the model and everything in this directory. So anything you put in this directory, we saw earlier, you can put a PNG file of a confusion matrix, and it'll end up in your model registry directory, which is nice. You can then look at that as well. But in this case, we're putting in the transformer object used in our model training pipeline. And maybe if we have an inference pipeline, we might want to use the same encoder object in the inference pipeline. This will ensure that we get no skew between the model-specific transformations in the training and then in the inference. So otherwise, it's the same code as we saw before. We can deploy this as a model to the model serving infra. I'm going to skip over this because we're going to cover this in the 5th or 6th lecture, I believe. But if we go down to the bottom, I think we can just run this one straight off. So this is Gradio that we saw from before, but what we'll see a little bit different is because when we're calling, it's a deployment here, so I need to actually, so the deployment seems to be working. I get a reference to that deployment object. Okay, let's have a quick look. Okay, it's giving me an error because I actually need a deployment. So let's go and get a deployment. I was going to cover this in a later lab, but we'll cover it here for the moment. So what I'm doing here is I'm actually deploying the model. So I'm deploying it to model serving infrastructure. So it's available on Hopsworks AI. The model will get deployed there, and we can just see if the model is running. It's already running. You can test to see if it works here. So just going to do a quick. It's going to call deployment.predict on the data, and we have to pass in this. It's a JSON object, so we pass the actual test data that we want to make a prediction with inside an array, and we pass then a JSON with instances before it. So it did predict here, in this case, Virginica, because we've actually done the inverse transform. So the inverse transform is you need the label encoding object to get back Virginica, otherwise we just get back the prediction. We can do that here by printing again, just with remove the inverse transform, and we'll just get the number. And I think Virginica is probably number 2 if I'm correct. Let's see. Yeah, so that's number 2. So and the same is true here in Gradio. If we run Gradio again, it's going to make the prediction, but the prediction will give us back a number, and we want to use this transformer object to convert our number back into the actual stringified category, because it's more, it's more human friendly and easier to read. So if we try this one here and press submit, it should predict Setosa, and if we make it slightly different, this should give us something like Verisign or Virginica. I'm not sure which one. It gives us Virginica. Okay, great. So that's a quick cover of model-specific transformations by using label encoders from scikit-learn. We put in our training pipeline. We've put it in our inference pipeline. Here we actually use a deployed model. So there are deployed models in Hopsworks. One thing to note then, if we go to Hopsworks, have a look at what happened there. So it deployed our model here. And it also created this thing called deployment we haven't covered yet. So you can see this model is now running. You can have up to 2 models that are running. You can stop them so that if you're going to deploy more models and you don't need Iris to be running in the background, I would just stop it. If you don't stop it, what will happen eventually is it'll get swapped out into an idle state, because it's using something called kserve in the background. So I think after 30 or 60 seconds of inactivity, the model gets swapped out, and then inference requests take a few seconds to start again. Okay. So let's go on. We've covered now the model-specific transformation. So we're going to go through the main part of the lab today, which is to run our training pipeline. We're going to feed the feature store with some features by running our feature pipeline from lab 2. And we're going to run it again. And we're going to run it again because it when we run the data, this feature pipeline, it'll timestamp the credit card transactions with today as the date. And when we do the batch predictions pipeline here, it's going to take features created in the last 24 hours. Okay, so let's start with running the model training example. We're going to check in Hopworks AI to make sure the data synthetic pipeline works. New rows are added, change some of the parameters. You can go ahead and change the fraud ratio if you want to have more fraud, for example. But in this case, I'm just going to go ahead and run the training notebook. Now, I actually started running it beforehand, but I'll walk through it so that we can see what's going on. So firstly, of course, we log into the platform. This part now is we create a feature view. So remember, in the lecture we talked about selecting features and creating feature views. In this case, what you can see here is that I have a feature view name called CC Transfraud. That's the one I'm going to create. I have a method here to create the feature view, and it'll create the version of the feature group as well. So in this case, it's this version is actually taking us the version of the feature groups. So it's getting a reference to our transaction feature group, the aggregated features feature group, the fraud labels feature group, and then what it's doing is it's going to use two transformation functions. So model specific transformations, min-max scalar, that we're going to apply to all of the numerical features, and then we have the label encoder that we're applying to the categorical feature, the category. And these two transformation functions are built into Hopworks, so when you're just getting a reference to them, and then you select which features each transformation function is supplied to. We define this in a dict, and this dict called transformation functions we're going to pass in here when we're creating the feature view. So the feature view is, remember, it's the selection of features that we want to use to train our model with and to make predictions with. So in this case, the features I'm using are from the fraud label feature group. We want the fraud label itself, of course, the date time of the transaction, and the TID for the transaction, so the unique identifier for the transaction. And the reason why we can keep that is that later, if so TID, we won't be training with the TID column, but we can include columns in our feature view that we don't use in training. We just need to make sure that we remove them when we create the train data itself, and when we also create our feature vectors. So we can call them helper columns. So in this case, TID is a helper column because when we make predictions in our batch inference pipeline, it's good to save the prediction logs. So to say, well, this was the prediction that was made, this was the input features, oh, and this was the TID as well, the transaction ID, or the credit card number, or the date time. So actually all three of those features, or columns I should say, we're going to include in our feature view, even though they won't be used as features for training models. So if we go back and look at these three feature groups, we have the fraud label, the transaction, and then the window aggregated transactions. We'll see them back here. So we have here the CC trans fraud, and this had the TID, date time, credit card number, category amount, country, and then we had this location delta, which was to help with geographic attacks. And it's a feature that's useful for saying, okay, two transactions happened at a long geographic distance with a short time between them, therefore they're suspected of fraud. So that feature captures that relationship. We also have aggregated features, so that the transaction volume, moving average, and standard deviation, the frequency within this 4-hour window of time. And then we have this location delta, moving average within this 4-hour period of time. And again, you can see we've got the credit card number and date time are in both of these feature groups. And the credit card number and date time are also in our label feature group. So we got the credit card number and date time. And this is how we're going to do what we call the point in time correct join. We're going to join on the credit card number, and then the correctness, the fact that we'll have no future data leakage will be ensured by the date time column in all three of these feature groups being the event time. So internally what will happen is that Hopsworks will select the feature values that are earlier than the label feature value. So the label column, in our case, this is our label feature group, and we have the date time for each transaction. So we've got this date time for each transaction. We have the label as to whether it's fraud or not. We have the credit card number. And we're going to pick the features from the other feature groups for a date time that is earlier than this date time or the same, but the closest the closest date time to it. So we'll take the feature value. If this date time, let's say, is 10 o'clock on the 1st of January 2022, and we have a transaction that happened at 9:59 and another one that happened at 9:58 on the 1st of January 2022, the latest feature value we'll pick when we're joining with this one here will be from 9:59 because it's closer to 10 a.m. Okay, let's go back and look at this. So these are the set of features that we're putting together. I'm going to now get a reference to my feature group view. Now the feature view is created. I created it earlier actually, and I just printed it out here. This print here is in fact, you can see it's a very long SQL query. This is in fact our point in time correct join, telling you what set of features are used and how they're joined together to create the feature view. But we'll go back and have a look at the actual feature view, which is here. So it's CC trans fraud, and we can see here that I have a fraud label that as a target. Let's go back and look at that. I didn't point that out. So we have this, when we create the feature view, we have the name and we have the query object that these are the set of features that we've joined together from the three different feature groups to make up the feature view. We have the name for this feature view, and then we have to identify which columns are the target variables or labels. And in this case, it's the fraud underscore label column. And then we also applied the transformation functions to a bunch of different features in the feature view. And that's this dict here telling us which ones. So these are all of the features. You can see then if you look at any individual feature, oh, this has this transformation function applied to it. And this is the feature group cc underscore trans underscore fraud 4 hours that it came from. So this is what we call provenance. We can see the provenance of any feature here in the feature view. That if we take, for example, the amount, it comes from the cc trans fraud feature group. And we can, click on that to have a look at it. It's opening it in a new tab, so I'll just close it and go back. And we can also see here that we have training data. So each feature view, you can create many different sets of training data with it. So you might create training data for a particular time range or a different time range. And each time we'll get a new version of training data created. So let's go down and I created one already. So I ran this one just earlier. And it created CSV file, and I got a reference to that training data. We have a quick look through the training data itself. And then this is the only thing I did a little bit different. So I removed these first three columns, the helper columns, TID, date time, and CC_num. So I call them helper columns because they help us when we're doing monitoring, when we're doing prediction logging and feature logging. To help, and also when we, for example, when we have outcome logging, if we know what a credit card transaction is actually fraudulent or not, we'll be able to link it back to the input features and the actual prediction, because we use the TID and the credit card number and date time to store the feature logs and prediction logs, and we're able to then join those two together. But what we have to do is we have to just ensure consistency between training and serving. So we're going to remove these three columns here in training, and we'll need to do the same thing again in our batch inference pipeline. And you'll need to make sure they're consistent. Okay, so so what do I do? Let's have a look here. So let's have a look at just how many fraudulent transactions are in this training data set. We've only 96. It's not that many, so it's a quite imbalanced data set here. And as you know, imbalanced data sets are not ideal for supervised machine learning. So there's a lot of work you can do to improve the prediction performance of the model you're training. I'm just using XGBoost here without any hyperparameters. So this is far from optimal. There's a lot of really good work you can do to improve the performance of this model. You can, upsample the rarer class in this case, and maybe downsample the larger class. Anyway, so now we're fitting the training data to our XGBoost model, and then after we're going to look at the performance. You can see it's a little bit slow because there's 50,000 or 201,000 rows of data, and it takes a little bit of time, so that wasn't too long. And then it tells us our hyperparameters here that were used in the training, and then we can look at the performance here. So performance, the F1 score, not great. Precision is 0.88 for the fraudulent class, but recall is only 36%. It's better than a baseline of random chance. The confusion matrix shows a little bit better. We got 35 correct of the suspected fraud examples. We got 61 wrong. So we missed 61 fraudulent transactions in this case. Okay, and then we got 5 more that we thought were in this case that we thought were negative, but they were in fact positive. Okay, let's go down and see what we're going to do next. We can print this report dict if we want to see the performance, and then we're going to register our model. So in this case, the model that we're registering, I'm just going to call register model to give it a name. In this case, we don't need, so in the earlier example with scikit-learn transformation functions, we stored the transformation function as a pickle Python object alongside the model. But in this case, we're using Hopsworks transformation functions defined in the feature view, so we don't need to store them or with the model in the model registry, because the feature view is going to actually, when we retrieve the features later for scoring, it will apply those transformation functions for us transparently. And it will do that both in batch inference and online inference, so you don't need to worry about applying them correctly and ensuring there's consistency between the transformation pipeline objects in your training and inference pipelines. It makes it a little bit easier. But often you might like scikit-learn, so you're free to go ahead, of course, and use that. Okay, so now we've saved the model in our model registry. We can go back and see if it popped up there. It's a model registry. Okay, so our model's here. It's the CC fraud one. We can have a quick look at it. And one thing we did was we saved some model metrics. So we can see the F1 score, precision, recall, support. And we can go back and see them here. So these were actually in the metrics object here. So this is our metrics object here. And we print out the report dict 0. So this was the report dict for 0. Okay, so this is not great. We're just showing the performance for the larger sample of non-fraudulent transactions. So you can improve this by printing out different metrics that for both classes, the fraudulent ones and the non-fraudulent ones. Okay, so that's the training pipeline covered. Let's go and look at the batch prediction pipeline. Now, I did already run the feature pipeline, so that was the second thing you need to do, but I'm just going to skip over it briefly and show you. When you run this feature pipeline, you can see it's going to create some start and end times for the transaction. So by default, it'll take a start time of 24 hours ago. So some time in the range 24 hours ago to the end time is now. So this assumes that date time is set up correctly, in this case on my laptop, and it looks to be okay. And you can play around with some of these parameters. So maybe you might want to increase the fraud ratio, not just pick a random number, but pick a fixed number if you like. And then it wrote some data to the feature store. So it wrote, you can see it wrote our 3 feature groups, to the transaction one, to the aggregated features, and then to the labels. One thing to note here is I set this wait for job false because it's writing to all 3 feature groups, and you can write up to 5 in parallel with Hopsworks AI currently. And there's no need for me to write, writing each one takes a minute or two because it starts a Spark job, and there's no need to wait for them one after another. I can just say wait for job false, and this will return as soon as the data is uploaded, and the job runs in the background. And the same for the second one, and then the last one I just waited for that one to finish, and then all 3 jobs will generally be finished by the time this notebook is finished. Okay, so let's go ahead and run the batch predictions pipeline. Now, what we can see here is that we're going to just basically retrieve all features that have been written between the start date and end date here. So the start date is 24 hours ago, anytime up to 24 hours ago, and the end date is right now. So it's going to look for any features that have any rows that have been written, any credit card transactions that were written in this time period. So the way we'll do it this time is it's going to use something called get batch data on the feature view. So the feature view can be used to retrieve online feature vectors when you're doing online inference, but when you're doing batch, you can use it also to retrieve a batch of data for scoring. And in this case, it's going to apply the transformations to our features before the data is returned. So the data will be returned as a data frame ready to score. So in this case, what we do firstly is we call get the feature view, and this is our CC trans fraud feature view and version number 1. Now the only thing that's a little bit different here is that when I have a feature view object and I want to get a batch of training data, in this case I use transformation functions in the feature view. So the feature view needs to know, well, this model that you're going to score now, this data, which version of the train data set, which train data set version was used to train it, because the transformation functions are going to use the statistics from that training data set. So it's going to know, for example, the mean value of feature for the training set. So in this case, we used version 1, which we can go back and see here. If we go back to the feature views, to the trans fraud, you can see I've got only one version of the train data set. So here you can have a look at it here. You can see it's split into train and test sets. It's a CSV file. And you can get some statistics for it. I think maybe were computed. So you can see these statistics are going to be used by the transformation functions that I mentioned before. Okay. Now the actual the way in which HopSerx retrieves these batch data is it takes our Python code and transpiles it into SQL, and we can see the complexity of these SQL queries here. It's quite long, and this is our data frame that got returned. So we've got this transactions data frame here. Now I mentioned before that we have 3 helper columns: TID, date time, and CCNum. So they're returned. The columns are consistently ordered between the feature view we use in training and the one we're using now. So we can, in this case, remove the first 3 columns just like we did before, because we're not going to use them. They weren't used to train the model, so they shouldn't be used to score the model. The next thing we need to, so let's remove those there. Okay, done. Next thing we need to do is download the model from the model registry. And we use the model registry object, which we got earlier on here. So this is the model registry object here. So when we log into HopSerx, we get a reference to our project, and we can say just get model registry, just like we call get feature store to get the feature store object. And what it does is it downloads the all of the files in our model directory to the local directory that I'm running here, where my notebook is running. So from within there, I know that it downloaded the pickled Python object from my model, and I can deserialize it. So I can unpickle it into the model object itself. Now, one thing you need to be careful of here is ensuring that you're running the same version of scikit-learn in the environment you're doing inference in, the same version that you use to train your model with. So I believe I am. And now we can make some predictions. So here's our predictions here. We can convert them into a data frame. We can have a look at some of the predictions. You can see mostly it's predicting that they're not fraud. And then we can write our predictions back to HopSerx. So we got an error here. So let's see what the error is here. Okay, let's I think I need to just rerun this one. Let's have a quick look again. Okay, it seems to be okay. So it's basically writing these 55,000 predictions back into HopsWorks. Now the predictions are for each transaction that happened. We're storing here the credit card number, the date, time of the transaction, and then the prediction as to whether it's fraud or not. And we also added then the batch start date to tell us which batch was used effectively for this prediction. And okay, so I probably should have let that run the background, but it's not. It's running blocking, so we have to wait for that job to finish. But let's move on and see what else we're doing here. So what do we want to do when we've made these predictions? Well, it's fine. We can write them back to the feature store, and then somebody who works on credit card fraud can then find the ones that have predicted that it's potentially fraud, so suspected fraud, and investigate those further. Maybe somebody who has other indications that transactions of fraud could look up this data set to see, hey, what did the AI tell us, the machine learning model? Did it tell me that this transaction was suspected of fraud or not? There's a bunch of things you can do. A very simple thing you can do for dashboards is you can basically, in this case, you can see it's predicting 42 counts of suspected transactions that are fraudulent. And we might decide, let's keep a little dashboard to see how many predicted fraudulent transaction credit cards we had in the last day. And that might be a useful thing for you to store. So that's what I'm going to do here. Create a graph of the number of suspected fraudulent transactions over time. We're going to have to wait for this ingestion to finish. It'll take about a minute at most. But let's have a look at what we're doing here. It's a very simple example. It's basically going to write to another feature group we're calling predicted fraud in this case. So the previous one was our fraud results, so the results of the predictions. This one is a very simple feature group called predicted fraud, and all it has in it is a date time, so whenever we did our batch inference, and then how many fraud predictions we made at this point, at this date time. So it's going to be very simple. We'll see if you're a business stakeholder, you'll be able to see from the example here how many of, let's have a look, how do we get here? We don't need to look at the inference. So we got, in this case, we can see on the day 288, we had 42? Let's have a look at the number again. It was up here. We had 42 counts of fraud, suspected fraud, I should say. So, over time, I just run this once, but if I ran this every day over a period of time, you would have then this bar chart with the day of the year and then the number of fraudulent transactions. So you could follow this and track its progress to see if there's more fraud happening today or less, or suspected fraud happening today or less. So that's basically it for the training part. Let's go have a look at the course. And for this batch inference pipeline, we'll need a workflow. So in this case, a GitHub Actions workflow. So we have one called Fraud Batch Inference Pipeline. And we did already the Fraud Features Pipeline. And this was from our first lab. This is the Iris one. So for this particular GitHub action, in this case, I turned off schedule because now we know how scheduling works and so on. Many of you will forget to turn it off and they'll just keep running jobs all day, every day. So when you just leave on workflow dispatch, then you're able to press and run the pipeline from here. So when you've workflow dispatch set up, you can go to your, in this case, the fraud feature pipelines. I changed the name. You can press this button, run workflow. So in fact, I can see a minor issue because what I did was I copied the pipeline from the last day. Let's have a look and go back at our actions here. Let's go back here. And you can see this one called the Fraud Batch Inference Pipeline. The name I didn't fix. So what I need to actually do is change this name. It should look like this because I saw on the other one. So I ran this earlier and it was fine, but I'm going to change the name while we're here. So let's have a quick look. VI kind of guy. So it's Fraud Batch Inference Pipeline. So I'm just going to change the name here to be Fraud Batch Inference Pipeline. Now I had some notebooks open, so I'm not going to commit and push this because it'll pollute the notebooks. I don't like committing and pushing all of the outputs of the cells, because then it becomes very hard to see diffs between your commits. I don't like that. But let's assume then this is called fraud batch feature pipelines. All it's going to do is what we've done before. It's going to run on the latest version of Ubuntu. It's going to check out our code. It's going to install Python 3.8. It's going to install the requirements. I don't think we have anything new to install here since Lab 2. And then it's going to run our fraud batch inference script, which runs our notebook. And we can have a quick look at that script. We added it. The script. Okay, maybe the script hasn't been added yet. So let's add that script. Okay. So we'll add the script over here. cd source 03 module. Oh, it is here. I just forgot to add it. Okay, so let's git add scripts run fraud. So scripts run fraud batch. So here we go, and you can see it's a little bit, there's a mistake in it. So let's have a go. Run fraud batch. So this should be 03 module, and then it's gonna our notebook is called for batch predictions. Let's make sure that that's correct. Whoops. C03 for batch predictions.py. So that looks correct. And I'm going to commit and push that in a second, and that's basically our GitHub action to run the batch inference pipeline. So that's basically it for the lab today. You know, we've firstly looked at scikit-learn transformations and how we can include those, what we call model specific transformations, in a training pipeline and an inference pipeline. Basically pickling the transformation object and putting it in the model registry beside the model. And then our inference pipeline, we download that transformation object, unpickle it, and apply the transformations before we make the predictions. We also looked at how we can do something similar with feature views and Hopsworks, but we don't need pickled Python objects. We just need to define declaratively which transformations apply to which features in a feature view. We defined a feature view for our credit card fraud example. We trained a model in XGBoost. We registered the model with the model registry, and then we had a batch prediction pipeline which downloaded the model, downloaded all the features created in the last 24 hours, and then it scored them and wrote them back to the feature store as a table. And we did some basic simple analysis of the number of suspected fraud examples in the last 24 hours. So here's a couple of things you can do as homework. In the Iris Flower example, you can extend it. We can take the 4 input features that are numeric and we can transform them with min-max scaler or standard scaler from scikit-learn. And you'll need to then save that to your model registry as you did before that transformation object. Now the second homework is that you can update the batch inference pipeline. So we did very simple limited analysis here. We just counted the number of suspected fraudulent transactions for each given batch inference or batch of data that we performed inference on, which was once per day. But we could compute the confusion matrix with the number of true positives, false positives, true negatives, and false negatives that we did from lab number 1. So that would be useful for our fraud prediction model, because we would then get a better historical understanding of how the model is performing. Is it missing fraudulent transactions? Is it calling transactions that are not fraudulent? How is it performing in general? So that's it. Thanks for listening to the lab. And in the next lab, we're going to look at user interfaces in a little bit more detail. We're going to look at Streamlit as well as GitHub pages that we looked at before, and Gradio here. And looking forward to covering that with you. Thanks.